Hi BC students. In this video we're going to be looking at the topic of logistic growth and decay. To help us understand logistic growth and decay, it might be good to start with just first exponential growth. Right, so for our background, exponential growth, we want to think about that in many applications. The rate of change of a variable y is proportional to the value of y. So that was a lot to be said there. Let me kind of go back and decode that. It says the rate of change of a variable y. And we're talking with respect to time. If we look at the rate of change of a variable y with respect to time, to decode that, we say that the rate of change of a variable y, which is dy dt over time, is proportional to, so we put equals, proportional to the value of y. Well, what that means is it's directly proportional, so we use this letter k to represent some constant. K is a constant, not a variable. So our y is changing, whatever y represents, perhaps growth of people, growth of animals, spread of a disease, whatever you want to call it. So the rate of change of a variable y is proportional to the value of y. Okay, so this is our derivative. This is the rate of change that tells us, gives us an idea of what the function y is doing over time. And because it's an exponential growth derivative, we can expect that that the function itself, the solution if you will, just grows without bound. So you guys know what an exponential function looks like, and it just increases without bound. Okay, so this is the derivative that represents that growth. Okay, now thinking about what we've been doing recently, we've been working with slope fields. That's one thing, sketching little short slope segments. One of the main things that we do in the area of slope fields is, given a derivative, we find its solution. So what we did to find the solution was we separated the variables and we integrated to get back to the original function y. Okay, so if that was to take place, if we were to separate the variables here, pull the dt over, divide by y, leave the k here, we can integrate and perform those calculus operations and get back to the original function. Okay, so this rate of change right here, okay, is going to go back to this general solution, y equals c, where c is yet another constant. Okay, and we actually end up with an exponential function, e, base of e, raised to kt, where k is some constant. Okay, so if you think about this equation, this general solution right here, it's exponential in nature. We know what that graph's going to look like. Okay, something, say, such as this. Okay, where c has the effect of vertically stretching or shrinking the graph, but it still maintains this kind of shape. And k has the effect, whatever number k is, of horizontally stretching or shrinking. So not big changes to the exponential graph, but certainly, you know, some stretching, shrinking, both vertically and horizontally. Okay, so if something grows exponentially, it would have this form of a derivative, and it would have this form of a solution in an equation. So this is exponential growth, where the function itself grows without bound. So now to tie in the word logistic growth decay. You know, exponential growth is unlimited, as you can see from this visual right here. Okay, but when describing a population, you know, of something maybe perhaps in the wild, you know, moose, I don't know, elk, whatever, coyotes, when describing that population, there often exists some upper limit L past which growth cannot occur. And if we think about that for just a second, you know, out in the wild there, you know, if you've got coyotes, you know, the environment would likely only sustain so many coyotes. You know, and then of course, you know, predator-prey situations, you know, the coyotes aren't going to increase without bound. This would not be a real good representation of coyote growth, if you will, because they wouldn't grow without bound. So when we think about that in some situations that we have a leveling off, okay, of our population, then we're talking about a logistic growth situation. In these certain types of problems, the logistic logistic differential equation looks similar to this, although a little bit different because of the situation where our population does level off. So our derivative for a logistic growth situation would look like this, but maybe a little bit different too. And actually the solution for a logistic growth situation is going to resemble this. It'll be exponential, but it'll look a little bit different too. And that's what we want to kind of focus on in this video. College Board has us be aware of the logistic growth function, what it looks like, and then also the logistic differential equation, the derivative that represents that situation. So that's our responsibility to know what those look like. So although similar to these, it won't be exactly like these. And so that's what we're going to look at here in just a second. So let's look at a logistic decay curve and a logistic growth curve. And I guess to help us kind of think about these graphs here, let's kind of think about, you know, when fish are put into a pond or a lake and you stock that pond or stock that lake, for the logistic decay curve, when you dump those fish in there, you know, that pond's not going to sustain as many as you put in there. There's going to be some die-off, etc. So for a logistic decay curve, let's go ahead and draw the first quadrant here. We're going to draw a graph of that population of fish. So I'll just let y of t represent the population of the fish. I could have done any letter for y. I could have done f for fish, whatever, but it's in terms of time. So this is the population of fish, and this is the time axis here. Okay. So let's say that they went and they dumped a bunch of fish in there, and I don't know, perhaps at time equals 0, this is t equals 0 down here, several thousand fish were dumped into this pond, and so this y-intercept represents that number, 5,000, 10,000, whatever. Okay. Well, over time, what's going to happen is the fish population is going to die off. Well, but the pond's still going to support some fish, so if we looked at a representation of the population of fish over time, it might look something like this, okay, where the number of fish is decreasing, but then we have enough, you know, of whatever the fish need to sustain a certain population. Okay, so this would look like this would be a representation of logistic decay. Okay, and so some things just to kind of consider right here is that this is your initial population. Okay, if I called this value, this y value L, L being the limiting capacity. Okay, think about this horizontal line right here at y equals L, whatever that number is. Okay, the fish are going to decline until they level off and they reach this number L right here. L is called your carrying capacity, what the environment, the pond can sustain. So that's kind of important to know that L value there. Okay, so let's think about what's being represented here. As time increases, as time goes to infinity, the y values, the fish, will approach our carrying capacity, our limiting value. So this would be a representation of logistic decay, where L is your carrying capacity. Okay, so let's look at logistic growth. All right, so now we're going to look at a logistic growth curve. Okay, so with same quadrant, dealing with first quadrant, it's a representation of the number of fish in this pond. So this time, let's just say that we're starting with an initial amount that's smaller than what we dumped into the pond over here, that we're trying to get this pond going. So we maybe dump in a few fish here and hope that the environment will promote growth. So here is our initial population at time equals 0. Okay, and so everything's going good and the number of fish is increasing, increasing, increasing. Well, in the early stages you can see that, you know, this looks to be exponential, but, you know, we're not going to have billions of fish in this pond, so at some point about right here, in my example, okay, the growth starts to level off. And this is the whole idea of logistic growth as compared to exponential growth that increases without bound. Logistically speaking, it starts out, the graph does, of the population, the representation, the model, starts out exponential, but it has to, level off at some point. You're not going to have billions of fish. So this is considered your logistic growth curve In situations such as, populations, disease spread, rumor spread, things such as that, they're more modeled by logistics growth curves than, say, exponential. They won't increase without bound. All right, so this is a logistic growth curve. What do we want to pay attention to here? Well, we want to pay attention to the fact that up here now, at this value L, okay, where I'm going to maybe draw in this horizontal line, that we have a limiting value called our carrying capacity, that pond's not going to support any more than this, say, L amount right here. Okay, so same thing over here, that same pond, whether you dump a bunch in, is going to die off until you get to this same L that's represented over here. Okay, if it increases, it's going to reach that same L from underneath. All right, so we want to pay attention to L. That's important. We need to be aware of that. Okay, and then we also want to pay attention to maybe where is the growth rate the greatest. Okay, where does the rate of growth occur the fastest, if you will. Okay, so looking at this graph, you can see that this logistic curve starts concave up and then turns concave down. Okay, it's increasing right here. The rate of growth is increasing. The slopes are all getting larger and larger, but about right here at this point of inflection, okay, what happens is that the slopes of the tangent lines, okay, the rates, okay, start to decrease. So where the slopes stop increasing and start to decrease at a point of inflection, okay, we have what we say is where the rate of growth occurs the fastest. And numerically, where that's going to occur is, interestingly enough, at half of the carrying capacity. So important to note is L, the carrying capacity, and perhaps a question that may be asked is, where is the rate of growth the greatest? And we can see right here that would be at half the carrying capacity. Okay, so coming down here, kind of putting some notation to what we see here. As time goes on, the y values, y of t, whatever, are going to approach L. So these are just representation of logistic decay and logistic growth situations. All right, so it's interesting to kind of look at the type of equation that would generate these graphs. So population of fish as a function of time is equal to, it's an exponential equation, L divided by 1 plus B. B is another constant. L is a constant, B is a constant. The exponential function raised to negative kt. So in this function right here, this model, the only thing that varies is time. Okay, is time. L is constant, B is a constant number, K is a constant number that we could determine based on a situation, a particular situation that we're given. This is the same equation right here as well that represents the population. Oh, I need a T. And just to remind ourselves about those constants down here, you might want to just put that L is called our carrying capacity, our limiting value. Carrying capacity. Right, taking a look at these equations in the comparison to the exponential growth equation up here, you can see that the both equations contain e, the natural exponential function. They're raised to some power kt, or as down here, negative kt. So they're similar in that they both contain an exponential function, but yet different looking, as mentioned earlier. So this is just the regular exponential growth equation, whereas this is a logistic growth equation. Right, now take a look at the derivative for an exponential growth equation. Okay, the rate of change of the population y with respect to time is equal to some constant times that population y. So our next look for what we need to do with regard to logistic growth and decay is to look at the derivatives of those situations. So that's what we're going to look at next, and it'll be similar yet different from the actual derivatives for exponential growth. Okay, if we have a situation that represents logistic growth or decay, the derivatives will be of this format right here. It's a rate of change of the population of y with respect to t. I think I might have hit something on the pen. Okay, and that derivative is equal to a constant of proportionality, k, times y, so it looks similar. Okay, but then we're going to multiply that by 1 minus y, the population, over L. Okay, so actually this derivative right here, okay, is a rate of change for the exponential decay. And then over here I'm going to do another column. The derivative for a logistic growth situation is the same thing. And that may seem strange that, you know, they're the same thing, but what happens is we want to compare y and L for just a minute. So when we have a logistic decay situation, the logistic function is decreasing, so the slope of the graph anywhere, any tangent line here, would have a negative slope. Okay, so we would want this derivative dy dt to be a negative number, okay, if we're talking about logistic decay. So how would we take this equation somewhere over here and produce a negative value that would represent a decay situation? Well, it's all about the comparison of y, the initial amount of your population, compared to the carrying capacity. Okay, so for decay, we can say that in this situation, we would have to know that y is greater than L. And just numerically, let's go through that in our brain. If y is a greater number than L, then the value of this fraction would be more than 1, and 1 minus a number more than 1 would give us a negative value, and negative times, this would be positive over here, a positive situation, okay, would give us a negative result. Okay, so when y is greater than L, we know that we have a decay situation. So likewise over here in this derivative, okay, well, what needs to take place with the comparison of y and L so that we have a growth situation? I'm sure you guys can see that my initial population, y, is underneath L. It's less than L. So here, if y is a value less than L, the value of this fraction would be less than 1, and 1 minus a number less than 1 would be positive, and that positive times this positive situation would give us a positive derivative, which means that our function is increasing, representing logistic growth. So looking at the topic of logistic growth or decay, there are certainly a lot of equations here, scary looking equations, and you might be thinking, do I have to memorize all of these? Well, let me give you the College Board perspective for an AP student and what we're responsible for. You're responsible for knowing about logistic growth, and that this is, you know, the type of equation that represents that growth, but you're not actually responsible for memorizing this formula right here for either situation. You're not expected to know the solution, if you will, for a logistic growth situation. However, we are expected to know that when we see this kind of rate of change right here, as I have listed here, that we are expected to know that this identifies a logistic growth or decay situation. So we do want to become more familiar with the derivatives than the actual solution equations up here. So it's worth, you know, kind of studying these two and being aware that the structure here is the derivative is equal to a constant proportionality times y, the function. So just note that here y matches with y, and that we have that product here times this other factor where we have 1, not 2, not 7, but 1 minus y, again, the population y, divided by L, the carrying capacity. All right? And that if you have decay, that this value y would be greater than L, and if you have growth, this value y here would be less than L. So this is our responsibility. We need to become familiar with and internalize and memorize, you know, these rates of change right here. Okay, so what's the kind of question that perhaps might be asked based on our understanding of this, you know, these derivatives right here? Well, this might be a good time for you to turn to your textbook and look on page 431 and look at problem 74. This is a good problem in the textbook that would be something similar to what you might see on a, you know, a AP test. So rate of change of p with respect to time is equal to 0.1 p minus 0.0004 p squared. All right, you can see there's a series of questions that you're asked about this problem. And the one I'm going to pick out is part B, find the carrying capacity. When you look at these derivatives, the carrying capacity is the denominator, okay, as long as we have the expression 1 minus y over L. So what that tells me I want to do is I want to rewrite this perhaps as a fraction instead of decimals. All right, so let's just change the format here. I'm going to say 1/10 p minus, and then what is this, 4 10,000ths, tens, hundreds, thousands, 10,000ths, 4 10,000ths p squared. Okay, well, I'm still not quite where I need to be. Notice I need to factor out the function, the p. It's available in both terms. Okay, and I want to factor out a constant of proportionality so that I have 1. So it appears to me that I'm going to factor out a 1/10 p from itself, because 1/10 p coming out of itself leaves 1 minus. So I'm getting it to be in this format right here. Okay, and so I know I'm going to have another p here. Okay, now it's a matter of dividing out 1/10 from 4 10,000ths. Or you might want to think, well, what do I multiply 1/10 by to get 4 10,000ths? Okay, or another way mathematically to think about what you're doing is you're dividing out 1/10 from 4 10,000ths. So over here, I'm just doing a little work. So what is 4 10,000ths divided by 1/10? So that would be a keep, change, flip situation, or multiply by the reciprocal. Okay, so let's multiply this by 10 over 1. So this 10 will cancel, cancels one of those zeros, so it looks like I'm going to have 4 1,000th. And I could pull the p back up here with the 4. I'm going to pull this down over here and rewrite it still. So we have 1/10 p, or p over 10. But you can see this and identify it as k real quickly if it's written in this format as opposed to p over 10. 1/10 p times 1 minus 4p over 1,000. Okay, we're still not quite ready to identify the carrying capacity, which is the denominator, because you notice that we have 4p in the numerator. All right, well, that just means we have to simplify. So 1/10 p times quantity 1 minus, divide 4 into top and bottom, it looks like 250. Okay, so what we've done is we've done some calculations, some changes here using some algebra, so that we've made this derivative, which we've identified as a logistic differential equation, a logistic derivative. We've created a situation to where it resembles this closely. Okay, so now we can real quickly identify the carrying capacity. So this means that L is equal to 250. Okay, so that's question B, find the carrying capacity. Okay, the other question I want to answer on problem 74 is D, which says determine the value of P at which the population growth rate is the greatest. Okay, so we saw that that's going to occur at half of L. So fastest growth rate is going to occur at 125. So carrying capacity divided by 2, which is going to be 125. So again, this was part B, and this was part D. Okay, and then next we meet, we'll just look at some more examples too of what College Board's expectation is for us regarding the topic of logistic differential equations.